So, the second topic I'm going to be talking about today is vector method for four-bar linkages. And so I need to establish some basics here. And this is actually a rather um, uh, high-end college topic, not necessarily master's degree or anything. I'm still a junior in college right now, but this is something that you learn in the engineering track. A lot of people don't even go that far into it because it's actually an elected course for my specific track of mechanical engineering, which would be the actual vein which would take on this daunting task. So I'll go over some of the basics because I wouldn't imagine too many people know what I'm talking about just right off the bat. But a four-bar linkage is actually a combination of three bars, but it's kind of a little bit abstract. We think of the ground as the fourth connector. So there's this imaginary bar here that's connecting the two joints that are grounded. So we don't necessarily need this bar because the ground is holding the two joints in place. But what this actually is it's a 1 degree of freedom system. And what that means is that if we move any of these pieces, then all of the other pieces will move exactly according to some formula. So if we were to send this guy moving in this motion, you can imagine that this guy would rotate with respect to this point, and this guy would go this way as well, eventually reaching some point possibly reaching some point where it can't go any further. Now there are some special ones where there's a tiny linkage over here, and then we got a bigger linkage, and this guy goes back and forth here, and then this guy spins around in circles. So that's a crank, and then we have a rocker. But we're just talking about four-bar linkages in general, and so this isn't anything specific, so we don't really need to get into the vocabulary. But the key idea here is that there's 1 degree of freedom, meaning that all of the pieces move together regardless of which one is the one we're actually moving. So whichever one we put force on, the other ones will move as expected. Now, if we add a 5th bar in here, that would actually ruin that idea. So if we had another bar like this and a connector here, then this could fall down due to gravity. It could whip up, and so it's hard to predict this, and we would actually have to be moving 2 of the bars with force in order to predict the position of this. So that's the basics on a 4-bar linkage, and I want to give some basics on vector notation. I did actually go over this a little bit, the Euler method, when I was talking about higher powers, and that's not a religious question. That's if we have a question of or it's a higher roots, I guess. So if we had the 4th root of 6, then you can use vector notation to find all of the roots of that number based off of the unit circle. And so if you want to look more into that, I'll put a link up in the corner to that video when I'm done and editing this. But essentially what the vector notation is if we have our 4-bar linkage, so we have some random configuration that just happens to look exactly like the last one I drew because it's the quintessential 4-bar linkage, then essentially what we're doing is we're saying that each of these linkages is a vector. So we're going to say that this is a vector, this is a vector, this is a vector, and then we're going to have one last vector coming from here to here. Now these vectors can go in any direction. Having these two coming out of the grounded point actually helps out a lot, just because it's not a relative position, but I'll talk about that a little bit in a second. I'm actually going to draw this with different color so that it stands out a bit more. Um, I know that's a little bit sloppier, but I want you guys to see where the vectors actually are. So we have to write an equation for this vector loop. So first off, that requires us to decompose a vector. Well, not necessarily decompose a vector, but to represent a vector with a notation. And so what we're doing is we're actually going to just write out some things. So we have the length of this is going to be A, the length of this is going to be B, the length of this is going to be C, the length of this is going to be D. So we'll assume that we know these things. And also we will have the angle here. This is going to be theta 2 actually, because this is link 2, but we're calling that A. This is just kind of general notation, so you can imagine that there is a theta here, and this will be theta 3, and then our last one is going to be from that vector to the ground. That's going to be theta 4, and so there's a theta 1 here, but we're going to start out with an easy case where this is actually a straight line, horizontal. So that theta is going to be 0, so we'll just keep this off to the side. Theta 1 is equal to 0. So like I said, we need to write out these values in terms of something that can be written out into an equation. And so if you know how to create things in vector notation, essentially what we're doing is we're using complex numbers. And so that may scare some people away, but essentially we're plotting things on the plane where the vector begins at the origin, and the horizontal axis is the real numbers, and the axis up here is the imaginary numbers. So imaginary means that there is a component j, and if they're pure imaginary, then there's only a component j. A complex number is the number a plus bj. Some people use I. That gets a little confusing in some engineering applications, so we tend to use j just because it stands out a little bit more to the little i's. This actually is very important in electrical engineering because I usually tends to stand for, I believe, current. So what we're doing is we're decomposing the vector. So we can imagine that our vector here is of length A at an angle theta. And what this actually means is that this vector is a e to the j theta 2. So what this is it's the Euler form of this. This can be decomposed into a cosine theta 2 plus a j sine theta 2, because j is the y, or the upwards direction, or vertical, I guess, because it can be down, and this coincides with sine being the vertical component of this vector. So we can write out this whole equation because this is an equation. If we consider this a loop, we can actually say that this comes back to the exact same spot. So in terms of vectors, it's equal to 0. So what we're essentially doing is we're following this loop, and if we're going along the vector in the direction that the vector wants to be going, which means the arrow's pointing that way, we say that it is positive, and on the contrary, if it's in the other, if we are going against the vector, then it's negative. So first off, we're going to start here at this point. We'll call this O2 and this O4 just for reference, for origin. So we will say that A times e to the j theta 2 plus, and so we're going to have our vector b times e to the j theta 3. Okay, so we're here. Now we're going backwards in accordance to this vector. So we're going to say minus c e to the j theta 4. And then once again, we're going backwards. So we're just going to say minus d. We can write this in just j to the 0. And so anything to the 0 power, it doesn't matter what this j is because anything times 0 is 0. Anything to the 0 power is 1. If you didn't know that, then there you go. And so essentially what we're saying is this is just d. I can actually erase that because I have an eraser. And so this whole thing is equal to 0. And the cool thing about this is we can use this to solve for pieces of information we don't have. So let's say that we knew how long all of these linkages were, all these links were. So we know how long A is, how long B is, how long C is, how long D is, and we're orientating this vector or this linkage A in such a fashion that it is creating this angle theta 2 with the horizontal. So what do we not know then? Well, we know A, B, C, D, and theta 2. There's we also know theta 1 just because of the orientation of how this works out. It's equal to 0. So there's two things we don't know, and that's theta 3 and theta 4. So, like I said, this is a 1 degree of freedom system, which means that if we know what orientation link 2 is in, or linkage A, then we can figure out what orientation all of the other linkages are in. So the way that we can do this, and you may be thinking, we only have one equation to work with. How can we solve for two different variables? The way that we do this is because this is a vector equation, and as you can see up here, this equation can be decomposed into different components. So each of these terms can be decomposed into its length times cosine times the angle added to its length times j times sine of its angle. And what I'm going to do is, well, the way we handle this is because half of the pieces of the equation will have a j in them, and the other half will not. Now, imaginary numbers and real numbers cannot be added together normally, like real numbers can be added to themselves. So essentially what this means is that both the pieces that have a j in them and the pieces that don't have to add up to be 0. They can't add together to be 0 because they don't add together. One's imaginary and one's real. So what we do is we actually split this up into two different equations because of that. We know that a cosine of theta 2 plus b cosine of theta 3 minus c cosine of theta. Oh, sorry, I forgot. There's a c in cosine, so I just started writing cosine. C cosine of theta 4 minus, and so this is actually important. I'm going to rewrite this in j to the 0. We have to remember that that this is actually here because the d is only going to apply to the cosine situation because the cosine is the horizontal component of all these vectors. Now, if you think about it conceptually, this actually does make sense because in order to stay at this point or end at this point, I guess, all of the horizontal components have to add up to be 0. So if we're saying that we're going to go cosine of A, or cosine theta 2 times A, then cosine theta 3 times B. We're here at the horizontal position of this point B. We're going to call this big B and call this big A. And then it's going to be minus our horizontal component of C. So we're going to get to here to O4, and then we're minusing D, which brings us all the way back to O2. So this works out. And the same goes for the vertical components. Now, I'm not going to be writing the J in here, because what happens is, since all of these components have a J in them, and they're all set equal to 0, that J actually pulls out and is divided. Well, obviously, if you say that everything's equal to 0, you can divide both sides by J. 0 divided by J is still 0, so nothing happens, and you have the exact same equation. Not necessarily the exact same, but the relationship is still there. So C sine theta 4. And we remember, we don't have this D component in our second equation. So we have two equations. Both equations contain these values we don't know, which are theta 3 and theta 4. Now, these don't have to be the values you don't know. You could be given these values and try to figure out perhaps what the length between the 2 points are. And so this would be pretty easy, actually, because what can happen is you can just bring this D to the other side. You have an equation equal to D, and then you just need to find whatever else you're looking for from the other equation, and you can plug it in and you'll get D as your answer. But the power of this vector form is that you can solve for two things. Now you can do this graphically. It won't be exact, assuming that you don't have an infinitely accurate protractor, or perhaps you are slightly off when you're drawing things. But this method is exact, and that's the beauty of it. So assuming that your given values and your assumptions are correct, you can solve for two different values at the same time due to the systems of equations. So this is very powerful. But what's interesting about this is that this vector formation can actually be used to find velocity and acceleration. So I'll show you what I mean by that. So I'm going to clean things up here, and I'm going to rewrite the original vector equation. So we had A e to the j theta 2 plus b e to the j theta 3 plus c e to the j theta 4 plus d e to the j theta times 0 is equal to 0. So this is our position equation. And so this is our original vector loop that equals the position. What's interesting about a 4-bar linkage is that when you look at the velocities of the individual points, these velocities are actually the, or I guess you could say the angular velocities, but the velocities add up vectorially in order to make a polygon. So this is an important piece of information, but this can be completely ignored when you're using the analytical method. What you can do is, since this is the position equation, if we normally had a position equation of s is equal, or s of x is equal to, I don't know, x squared, what would we do to find the velocity of this position equation? Well, v of x would be equal to the derivative of this. So that would be 2x, and then our acceleration would be the derivative of the velocity, which would be 2. And we can use the exact same method. So if we just clean things up here, sorry for the delay. What we can do is we can say that we want to take the derivative of each of these pieces. And so it's nice because they're a linear combination. We can just take the derivative of each of them, add them together, and we get the derivative of the whole thing. So the derivative of this piece, and so first off, we're going to assume that none of these linkages are increasing in length. That's important for this case to keep things simple. So if this a is a constant, then all we're taking the derivative of is e. And what's nice about e to anything is that the derivative of that is e to that same thing times whatever the derivative of the thing in the power is. So we're going to say that this is actually, if this is our independent variable, then we're going to have a j e to, oh, actually, sorry about that. So we have to take the derivative of theta. And so the derivative of the angle is the angular velocity, just like the derivative of the position is the regular velocity. So this is going to be a j omega 2 e j theta 2, omega being the angular velocity. So if we had our vector here, this would be the rate at which the rate in radians per second at which this vector is changing. So that's one term plus bj omega 3 e to the j theta 3 plus c j omega 4 e to the j theta 4. And this last term is completely constant. Like I said, nothing is changing in length here. So the derivative of d is 0. The derivative of e to the j 0, which is 1, is 0. So we don't have anything else in this equation. We've actually reduced our equation down to 3 terms. Now, these 3 terms are relatively complex, not to make a pun here, but they are a little bit easier to work with than having our 4 terms. So let's look at what we're working with. We've already figured out what theta 3 is and theta 4 are from our position analysis, and now we have a new vector equation. So we can then again solve for 2 different things. So let's say, since we're controlling our linkage A, we can actually adjust the value of what the omega 2 is. Well, that only leaves 2 things we don't know. That's omega 3 and omega 4. So once again, and I'm not going to write it out just for time's sake, but we can decompose this into sines and cosines. Now, there is something interesting I want to point out. We have to remember that e to the x to the jx is equal to cosine of x plus j sine of x. So we have to remember that this is what we're working with. So then what is j e to the jx? Well, that just means we're multiplying this other side by j. So if we multiply cosine by j, we multiply this sine term by j, that gives us j squared. So j times j, this is just imaginary number times imaginary number. If you're up to date on your imaginary numbers, you know that an imaginary number times an imaginary number is just makes -1. So or if you take the unit imaginary number and multiply it by itself, it gives you -1. Because the way that we define imaginary numbers is that j is equal to the square root of -1. So if we square j and square this side, we get -1. This new term, we can actually take this j out of here when we decompose it and actually switch up which side has the j and which side has the real numbers. So this would actually be j e to the jx is equal to negative sine of x plus j cosine of x. And this actually makes sense when you think about it graphically, because if we have our vector here, and this is our linkage, we want to think about what the velocity of this vector is. So if we have our omega 2 going in this direction, The velocity of anything rotating about a fixed point is exactly perpendicular to the radius created by this vector. So this is perpendicular, which means that it's going to be that the horizontal direction is going to be actually 90 degrees offset, and in this case going in the opposite direction. So that's why we have this negative. And the vertical, or I might have said that backwards. So the horizontal component is going to be offset by 90 degrees because of this j, because we're actually switching sine and cosine, and it will be in the opposite direction. And then the vertical component will actually also be not offset by 90 degrees because now it's cosine, and it's going to be in the same direction for the velocity. So we have the, you have to keep this in mind when you decompose it. So actually the equations will be kind of flopped. But this doesn't really affect too much because this negative is going to be able to divide out since it's equal to 0. And this j is going to divide out since it's equal to 0. So essentially it's about the same equations. It does get a little bit more interesting when we go to acceleration. So I'm going to move on to acceleration. Actually, let me just grab this equation for time's sake. Copy that. And now we're going to clean the board here and paste that guy back in. So you have to remember, this is our velocity equation. If we want acceleration, we then have to derive this again. And so that's not too difficult. It gets a little bit more confusing, though, because this omega can actually be, it is actually derivable. So it's not a constant value. It's something that we can change because it's the angular velocity of our independent variable theta. So each of these components, when we take the derivative, is actually going to have two different components. This is due to the chain rule because we have a differentiable value multiplied by another differentiable value. So we're going to first differentiate the first term and multiply it by the regular second term. So this will be aj alpha 2, so this is the angular acceleration, ej theta 2 plus a, and so remember that we're not touching e, so all the other constant values stay the same. But here we're differentiating e to the j theta 2, which in the velocity, you'll remember, took a j down. So what we're actually going to do is that is going to be multiplied by this other j and become a negative 1. So we're going to have negative a omega 2 squared, because we're differentiating this theta 2 again, e to the j theta 2. So this is going to be done for all of this. And actually, this was supposed to be subtraction. I think I wrote that incorrectly when I was doing that before, just because of the way we were oriented originally with our original problem. So this is how we're differentiating these two terms. And so this is actually interesting because it claims that there's two different things determining the acceleration of this point. And if we think about that graphically, then it actually does make sense. So we're going to have a term that is perpendicular, because we remember that this multiplication of a j does this. So this is going to be our first term right here. And we're also going to have another term which is going to be in the direction of the position, but negative. So from this point, it will actually be down. And I'm going to grab another color here. So we're going to have another vector here. And imagine this is a 90-degree angle. So what does this mean? Well, it's saying that there's always an acceleration towards the center. And if you think about that with any circular motion, this is true. If you have something that is on a rope and you swing it around, it doesn't accelerate away from the center. Um, it stays on that circular path, but in order to, if it's going straight, it wants to go tangentially, and there's a force that's pulling it to curve it around at the exact same radius, which means that there is a force applied, and F equals ma. So that means that there is actually a acceleration towards the center of a rotating body, a body rotating around a point. So there's always going to be this acceleration that I've written in red going in towards the point. And what's interesting about the vector notation is this right away tells us that this acceleration is actually due to the angular velocity and not due to the angular acceleration. So we have another acceleration, which is actually how it's the change in the angular speed. And so this makes sense. If we're putting a force on it this way, it's going to want to whip faster than it already is. And then we have the second term, which is pulling it in towards the middle, which means that it stays on a circular path. So this is true for all of the points. And so what we find is that we can then, we know what all the omegas are, we know what all the thetas are, we know what all the linkage lengths are, and we can solve for the alphas, assuming that we know the acceleration of at least one of them. So this means that, so we'll have an alpha 3 and we'll have an alpha 4. So this is vector notation, and it's very powerful. This is what people use to program computers for simulations. Now, there is a little bit of simplification for specific situations. Like I said, there are different orientations of 4-bar linkages, whether they be crank sliders, crank rockers, double rockers. I don't think there's any double. Actually, there is double cranks, but they're kind of stupid. But you can solve this out once, plug it into a computer, and then every time, all you have to do is give it the position of this vector, and it'll tell you where all the other vectors are right away, because there's just a simple equation that it has to solve. And like I've said in the past, computers are very good at solving equations. So this is vector notation. Now, there are some interesting things. So like I said, in this case, none of the linkages are gaining length, or gaining or shortening in length. So if we just had, let's say that this guy was a slider that's 90 degrees with respect to this link, and it's sliding along this bar. So we can imagine that this is rotating, and then this guy slides in as that pushes out. Anyways, what we do is we actually, I'm going to grab blue. Just maybe, yeah, we'll go to blue. We can say that there's a vector here, and there's a vector here, and there's a vector here, and of course there's a vector here. And we'll imagine that that's horizontal, even though I've done a poor job of drawing that. So the difference with this situation is we have our A, we have our B, we have our C, we have our D, we have all of our angles. The difference is that B is changing. So B is not constant, and we now have to consider that change. What that means is when you differentiate the original B term, when we have e to the j theta 3, and we differentiate that, we have to use the chain rule here. So that means that we have our b dot, as we say. This means that it's the time derivative. So b's change with respect to time times e to the j theta 3. So you'll notice there's no j, there's no omega. And then this will be plus, so it'll be plus b, sorry about that, bj omega 3 e to the j theta 3. And so this is two terms, and you can only imagine it gets a little bit more confusing in the second in the second derivative. So I'll go ahead and write it out. So both of these have multiple terms that need to be differentiated with the chain rule. So it's going to be a long process. We have our b double dot, which is the it's the acceleration of the length of b, or you could think of it as the acceleration of this rocker, essentially. E to the j theta 3 plus b dot j omega 3 e to the j theta 3, and we're going to have plus, we're going to differentiate b first, so we'll have another b dot j omega 3 e to the j theta 3. Now these are the same thing, I'll get to that in a second. Plus we're going to differentiate our omega, so we're going to have our b j alpha 3 e to the j omega 3, and our final term I'm going to write below here is our inwards acceleration. So that's going to be b j, that's going to be omega, oh sorry about that, there is no j in this term because we've put the negative sign here because there's j squared. So that's going to be omega 3 squared e to the j theta 3. So what we have here is we have our normal acceleration, we have the acceleration of our slider here, and we have these two terms. And so this comes together to be 2b dot j omega 3 e to the j theta 3. And so this has an interesting name. It's actually the Coriolis acceleration. Essentially what it says is if you're here and you're watching this guy, it's going to have an acceleration perpendicular to its actual travel. And so this acceleration doesn't really exist, but it's something that you'll witness if you yourself are in a rotating reference frame. So essentially, let's say you had two people sitting on a wooden plank. I can draw this out actually. So if you have a ball here and there's a plank going across, you got Johnny and Johnny's got a ball, and then you have Sally over here. Sally's got some long legs. Sally's waiting to catch the ball, and this whole thing is spinning in a circle. Johnny tries to throw the ball to Sally, but by the time the ball gets to where Sally would have was originally, Sally's now over here. So in terms of Johnny's perspective, it seems as though, so we're gonna look down the perspective of Johnny's line of sight to where Sally was. It seems as though this ball we have is taking this curled path out to the side because he is in a rotating reference frame. You can try this on your own. You will get somewhat dizzy, and what essentially you have to do is you have to throw the ball here so that it curves to where Sally will be. So this Coriolis acceleration is there, but it only exists in a rotating reference frame. And if you want to feel it for yourself, get one of the merry-go-round things at a playground spinning really fast and try and run on it. When something hits you very hard in the side, that's Coriolis acceleration for you. So that is vector analytic notation, and so I hope this was explanatory and thorough, and I will be moving on to my random drawing.